It's just logs, right? All right. Today we're actually not going to use logs, but then we will. The rest of this unit will be. Last call for questions before we just jump right into the notes. All right, pass up your homework then, please. Thank Okie dokie. Notes. All right, you guys, we're going to get back started and we're going to go into notes now. We're going to do something called the Trapezoidal Rule. This is actually going back. This is going back to approximating area under the curve, so approximating definite integrals. Let's remember we had left rectangle approximation, right rectangle, midpoint approximation. Now we're going to have something called Trapezoidal Rule, which, crazy as it sounds, is going to use trapezoids. And I know it may seem like, well, wait, but we already know how to use it to find a definite integral. Why do we need to do this stuff? But do we? Remember, to evaluate a definite integral, the first step is to find the antiderivative. What if you're trying to find the antiderivative of a function that you don't know the antiderivative of? Or, what happens a lot of times in the real world, we don't have actual functions. Instead, we have data that we've collected. And you'll see an example at the end of the class like that. So there still is uses for these approximation methods, even though we don't, even though we do have the fundamental theorem of calculus that can evaluate definite integrals for us. So there is a point to this. There really is. So yeah, let's just jump into it. Let me pose a problem and we'll see how this works. So we are going to approximate the area under f of x equals 1 over x cubed plus 1. I just lost my train of thought. Oh, using trapezoidal sums with 3 subintervals, oh my gosh, of equal width over the interval from 0 to 3. I actually didn't mean that function. Let's make it a little easier. We'll save that function for later. Let's just do x squared plus 1. That way we can draw the graph. Sorry about that. Okay, so let's draw a picture to represent this. I'm going to do something similar to what I did before. Let's see, if I'm going from 0 to 3, then on the y-axis, and I know I got to go from 1 to 10. So I can count by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll go one more just for fun. On the x-axis, all I need to do is go from 0 to 3, but I'm actually going to spread this out a little bit. So I am going to let every 2 squares be equal to 1 on the x-axis. So there's my graph setup. And we'll graph this function. Let me use green. So we have a point at 0, 1, at 1, 2, 2, 5, and 3, 10. Oh, that's crummy. Oh my goodness, I can't draw a parabola. There we go. So we're trying to find this area right under there. So let's shade that. So we're going to approximate it using trapezoids. So just a quick reminder. Remember, if we were going to use left rectangles, we would go ahead and start at the left endpoint and draw our rectangles. That would be left rectangle approximation. If we were going to use right rectangles, we'd actually use the right endpoint from each interval and draw our rectangles that way. If we were going to use midpoint, we'd actually use the midpoint and draw our rectangles. And we'd have these, but we're not going to do any one of those. We're going to do something called Trapezoidal Rule. And what that does is it actually uses both endpoints and then just connects them. So our first trapezoid will look like that. The next trapezoid connects these 2 points. So this one's a little harder to see because it's actually doing a fairly good job with straight lines of following the curve. Obviously it's not exact, but it's definitely much better than the other ones of following the curves. So then there's our trapezoidal sum. So any questions just how I drew it? Does that make sense? So now let's actually find this. Now, I kind of gave it away. I should have asked actually first. We are doing equal width, so we do have a formula for finding delta x when our subintervals are equal width. Anybody remember what that formula is? Yeah. B minus A over N. And so in our case, if we plug in actual numbers, A and B represent the interval from 0 to 3. So it's 3 minus 0. And we are talking 3 subintervals. That's what N is. So we can see delta x is 1. And you can see that on the graph that I did. I just went up by 1. So my x values changed by 1. So, yes, Grace. That stands for the number of subintervals. So that's coming from this. And then the 0 to 3 is what gives us the numerator. Any other questions? Okay. Now we are doing trapezoids and we are talking about area. So we're going to use the formula for the area of a trapezoid. Let me actually just scroll a little bit here. Area of a trapezoid. Anybody know, just in general, like not in terms of calculus, but going back to your geometry days, what's the formula for the area of a trapezoid? Zoe? There is an over 2. There's lots of different ways to write it. I'm going to write it this way. Yes, exactly. Excellent. That's it. And if we look at this first trapezoid, I'm just going to call these T1, T2, and T3 for our different trapezoids. So for T1, where's the height? Anybody know? I heard the across, and so it would be, yeah, exactly it. It's the width of your subinterval, just like Nate said. So remember, in general, in a trapezoid, this is our classic trapezoid that we often think about when we hear the word trapezoid. So by definition, the bases, the B1 and B2, those are the parallel sides, and then the height represents the distance between the parallel sides. In our picture, it's just a trapezoid on its side, if you want to think of it that way. Here's the parallel sides right there. And then the distance between, the height, is our delta x. Excellent. So, if I go back up here then, for T1, the height over 2 is just going to be delta x over 2. And then how do I find B1 and B2? Carly?
On the y-axis.
Exactly. So our B1 and B2 are these two lines here. The length of this first line corresponds to f of 0, and then the length of this one corresponds to f of 1. So it's f of 0 plus f of 1. And then we'll just evaluate that. So any questions where that's coming from? Because then it's really easy. We already said delta x was 1. And we can see f of 0 is 1 and f of 1 is 2. So it's just 3/2. So any questions finding T1? What I want you guys to do is try to find T2 and T3. Anybody have an answer for T2? Grace. Perfect. Excellent. 7/2 it is. And T3? Carly. 15/2 it is. There's the work right there. Any questions there? And then, all we have to do is add them up, and we got it. Before we do that, let's remind ourselves, area under a curve we can represent with a definite integral. Oops. So in this particular problem, what would the definite integral be that represents the actual area under the curve? Anybody remember? Sophia? 0 to 3. Perfect. That's exactly it. That represents the actual area under the curve. We are approximating it with the trapezoidal rule, which in this case is going to be 3/2 plus 7/2 plus 15/2, which is 25/2. So that's our approximation. Ta-da! 12.5. So that's trapezoidal sum. Any questions about that? Now there is a formula that you can use if your widths are equal, like they were in this problem. So let's go ahead now and take this and try to condense it down to an equation. So I'm going to go back up here to our work. What I'm going to do is I'm going to take this form of T1 and T2 and T3. And I'm going to put them all together, and let's see what happens when we do that. So down here, oh my goodness. All that stuff that I highlighted above, that's where I'm going to get all this stuff below. So here's what I mean. In this case, the trapezoidal sum with 3 subintervals was equal to delta x over 2 times f of 0 plus f of 1. That was T1. And then we added T2, which was delta x over 2 times f of 1 plus f of 2. And then we added T3, which was delta x over 2 times f of 2 plus f of 3. Now that we see it all together, we can condense this thing down a little bit. Any questions where I'm getting all that from? Every term definitely has a delta x over 2, which, remember from the formula for the area of a trapezoid, that's the height over 2. Every trapezoid has height over 2, so let's just factor that out. And then if I factor it out, I'm going to have these 3 things left. And if I look at those, I actually have some like terms that I can combine. I have 2 f of 1s and 2 f of 2s. So when I fully condense everything down, it's going to look like 1 f of 0 plus 2 f of 1s plus 2 f of 2s plus f of 3. And that's about as condensed as I can get. But at least that's more condensed than it was above. And we're going to kind of generalize this. But if you look at this, this actually makes sense. Again, every trapezoid has, for the formula for the area, has height over 2. So it makes sense that we have a height over 2 on everything. And then all of the y values get doubled except for at the endpoints. But that also makes sense if you look at the picture above. At the picture above, we can see that f of 0 was only on one trapezoid. But then f of 1 was part of 2 trapezoids. F of 2 was part of 2 trapezoids. Everything's part of 2 trapezoids except for the values at the ends. So it makes sense that everything gets doubled except the things at the ends. So we're going to generalize this into this formula here. The trapezoidal sum with n intervals of equal width is T sub n delta x over 2, that's the height over 2. And then I'm going to say f of x sub 0. But then we double f of x sub 1. And we double f of x sub 2. And we double, and we keep doubling until we get to f of x sub n minus 1. And then we have our endpoint, f of x sub n. And boop, 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 boop. That's it. Now, be very careful, because this is only for equal widths. For your homework tonight, a lot of it is, in fact, the vast majority is equal widths. Is that a hand up, Sophia, or are you stretching? Okay. So most of it is equal widths. You can use this formula. On the AP exam, I believe, again, I haven't seen much of the multiple choice because they don't release that every year. But when trapezoidal sum shows up, it'll be equal widths. However, on the FRQs, and we're going to see a free response question today from the AP exam, it's almost always not equal widths. So I'll show you what to do when it's, actually when it's not equal widths, you basically have to go back and do what we were doing here and do each triangle or each trapezoid separately. The delta x will be different on each trapezoid, but then you still take the y values and stuff. Lost my train of thought. What was I going to do? Yeah, I think we're ready for it. Let's do an example. What we're going to do is we're going to do an example with equal widths. Then I'm going to give you a copy of an FRQ from 2010. And we're going to look at that one together. And then in the meantime, I'm also going to show you some stuff on the calculator. So speaking of the calculator, if you got a calculator, take it out. And if you don't have a calculator, go get one. Okay, we're going to approximate this definite integral using trapezoidal sum with 3 subintervals. Now, the 3 is boring. How about 7 subintervals of equal width? Yeah. 3 was boring. 7's going to be tedious. But don't worry. We got our calculators, and that's going to do most of the grunt work for us. All right. So if you think of the formula, it does say equal width, so we get to use our formula. There, I'll scroll down a little bit. So there's our formula right there. We need a delta x. Can anybody tell me what delta x is going to be? Nate? 3 5/7? Is that what you said? Oh, just 5/7. Yeah. I don't know why I heard 3. That's why I was like, what? Yeah. B minus A, 9 minus 4, over N, which is 7. 5/7. So then, this is where the tedious part comes in. If we think about our x sub 0, x sub 1, x sub 2, and so on, all the way up to x sub n, that's basically going to take, I'm not going to try, who knows what the graph of 1 over x cubed plus 1 actually even looks like. It doesn't matter. What matters is, can we take the interval from 3 to 7, nope, I don't know why I'm saying 3 to 7, from 4 to 9, because that's the interval on our definite integral. Can we take the integral, the interval from 4 to 9 and cut it up into 7 equal widths? And we can. We know what to count up by each time. To find the next value for the next subinterval, does anybody know what problem I would have to work out? It's actually right there in front of us, believe it or not. Remember what that delta x means. We're going to start at 4, and we're going to go up by delta x 7 times until we get to 9. So I'm going to have to take 4 and add 5/7 to it. And that will get my next value. And then I'm going to add another 5/7, and then I'm going to add another 5/7, and I'll keep adding 5/7 until I get to 9, and that should give me 7 subintervals. I'm going to make life a little easier. Let's just get a common denominator right now. So 4 is the same thing as 28/7. And then from there, I'm just going to keep adding 5/7 to it. And I'm going to get rid of that because I don't actually know. Anyway, I'm going to keep adding until I get to 9, which is the same thing as 63/7. So we get 33 sevenths, then we add, and we get 38 sevenths, 43 sevenths, 48 sevenths, 53 sevenths, 58 sevenths, and there's my 63 sevenths, which I'll actually put down here. That's the same thing as 9. Dun, dun, dun. And sure enough, if I count 1, 2, 3, 4, 5, 6, 7 subintervals. It worked! It's like this math stuff, there's something to it. So that's how I'm cutting up my interval from 4 to 9. I'm using those values, and those values basically correspond to my x0, x1, x2, and so on, all the way up to xn. So now, let's plug it in. Now, nowhere on this problem have I actually defined what f of x is. I'm going to go ahead and define it, and that way I can use the notation of just saying f of x each time. What is my f of x in this case? Say it again. Yeah, 1 over x cubed plus 1. It's just the integrand. So, now I can say that my trapezoidal rule using the 7 subintervals is, and now I use the formula. The formula up here says delta x over 2, and then I'm going to do all the function values, doubling everything except the endpoints. This is where the tediousness, part of the tediousness comes in. So delta x over 2, delta x, and if you want to make sure you don't make any silly mistakes, this is one of the few times I will say it's fine if you just write it like this. Delta x is 5 sevenths, and it's over 2. What? You don't have to write it as 5/14? No, it's okay if you just do that. And then it's f of 4 plus 2, f of 33 sevenths plus 2, f of 38 sevenths. Do not take any shortcuts on this part. If this was a test and you took shortcuts, I will mark you wrong. I know this is tedious, but it's not hard. And remember, just keep doubling until you get to the end. And then you don't have to double. Any questions? What I just wrote. Like, how did I get all this? Because then the beauty is we're going to have the calculator do it for us. And we're going to make it as easy as we can to type in on the calculator. But any questions on this so far? All right. So I'm going to go ahead and open up my calculator. And here's what we can do. And so now be ready, and if you have not been using your calculator very much, I mean, I know I keep calling it a calculator and I don't want you to, but try to get used to using some of the functions on it. So if you haven't been using it very much, try to get used to doing some of the stuff that I'm showing you, because, in fact, I'm going to encourage you on tonight's homework. Please use your calculator. Practice what I'm about to show you, because you want this to become muscle memory. So what I'm going to do is this. On the AP exam, there's 6 free response questions at the end. You take multiple choice part, and then you take the free response. And the way the free response questions are done, the first 2 questions are calculator based, and you get 30 minutes to do both questions. So on average, about 15 minutes per question. The last 4 are no calculator, and you get an hour. So again, about 15 minutes per question. Those first 2 questions that are calculator based, they will always give you some function, and that function is going to be used multiple times in the problem, like in your work. So the easiest thing to do is go to your y equals, And we're going to enter the function in right there. This isn't a very complicated one, but you'll actually see when they give you these, it's like it takes a while to type them in. It's kind of a pain. Put them in your y equals, and that way you can pull them up all the time. So 1 over x cubed plus 1. Oh, I don't want that in the exponent. I keep forgetting that the new operating system does that. So we have this. Now, what do you guys think about how I entered it in? Does it look good? Oh, good. I'm glad to see you not like it. What's wrong with it? Yeah, right now that plus 1 at the end is not in the denominator. Now, I don't know if you guys have noticed, if you've run into this. So you go back, you're like, oh, okay, I want to put a parenthesis in there. When you type parenthesis, and then it starts writing over what you wrote. And it's like, damn it, do I have to retype everything? Urgh! And the answer is no, you don't. I'm going to put the x back there. I want to insert the parenthesis above the delete key. In blue on my calculator, it's insert, I-N-S. If you hit second insert, your cursor actually changed. I don't know if you noticed that. And now I actually can insert a parenthesis and it shoves everything over. So if you ever want to insert something, there's your trick for doing that. Okay, so now I've got my function entered into y1. Now I'm going to quit out of that. So I'm going to do second quit to quit out of that. Now, if you're using one of my calculators, you may already see it entered, although we had a different delta x, so you're going to have to re-enter stuff. But basically, I am going to type in all of the stuff that we have in our notes here. So the first thing I have is a 5 over 7 over 2, so I'm going to do 5 over 7 over 2. Notice I'm putting that double set of parentheses. One set of parentheses for the fraction on top, one set of parentheses for the delta x over 2, the whole fraction. And then I want to tell my calculator f of 4. That's the next thing we had written on our papers. Our function is in y1, so I'm going to do y1 of 4. Now there's two different ways you can get the y1. One way is if you go to vars, underneath your cursor keys, if you hit vars, and then scroll over to y-vars, and then it's a function. And it's number 1, so I'm just going to hit 1 again. So there's y1, and then I literally just do of 4. And then again, the next thing was f of 33/7, but I want to double it. So I say 2, vars, scroll over, y1 of 33/7. And then we just keep doing that. Now that's one way to get the y1. There is another way that technically is one keystroke less. It's hidden though. So if you look at those top row of keys on your calculator, like where the y equals, Windows, Zoom, and so on, above them there's a F1, F2, F3, F4. We're going to go to F4. But that's in the alpha color. So I have to hit alpha, F4, and see it pulls up that menu. And then Y1 corresponds to number 1, so I can just hit 1. And that's another way. But actually I need my plus sign. I've gotten so used to the years, because they actually added that in later. I use the vars button. It's so quick. But you can use whichever one you want. Doesn't matter. But now you can see the tediousness of it, but we're just going to keep typing this in. There's no other shortcut we can take. Oops, forgot my parentheses. And I don't have a touch screen, so I have to use a mouse, and this stinks. But just keep going, and we'll see if we get the same answer. Oh! Can do. Oh, no, I hit... Oh, well. You guys know what was going on, right? I'm not going to even try. But does somebody have an answer? And then we can compare and make sure. It's very easy to just make a silly mistake on keystroke, so we'll just see if multiple people got the same answer, and we'll put it here. Does anybody have an answer they want to share? Carly?
I got 0.025.
0.025. Anybody else get 0.025? Okay, all right, we'll go with that one. Thank you. Ah! And there you go. So that's a trick you can do. Here's one more thing that I do want to do before we put our calculators away. Is let's find out how far away our answer actually was. So let's see what happens when we hit Math 9. So Math button is over here on the left, below the alpha button. And look at choice 9, FNINT. What? Look at that. It's a way to evaluate a definite integral. What? And the definite integral that we are doing, we are going from 4 to 9. And then again, we have the function already entered in y1. So I can just do vars over to y1. This time we're not actually plugging in a value though, so just leave it as y1. You don't want to plug anything in. And then x. And there it is. Does anybody have the old answer on their calculator? Can you read off like all the digits?
0.0253460843.
Oh, so 4853. We were pretty close, weren't we? Not bad. So, there you go. Any questions about that? Math 9 is going to be a friend of yours. Math 9. Math 9 and Math 8. I showed you briefly Math 8 one time, but we didn't really use it. If you do Math 8, that's the way to evaluate a derivative at a value. It doesn't actually find the derivative, but it finds the value of a derivative at a given value. All right. Let me go back here. So, So I went ahead and just put the answer there that you guys got on the calculator. So for tonight's homework, seriously, write this stuff out. Although I think they're nice to you. I think they only give you like 4 subintervals at most, not many. This was with 7. It was kind of tedious. But you do have to write all this out. But then seriously, use your calculator. Get used to plugging this in. Hopefully even after this one problem, you got really used to going whatever method you were getting your Y1. But just get used to it, because it's going to be a nice trick you can use. Trying to think if there was something else before we moved on. No, I think that was it. Any questions so far? Is that a question, Sophia? Yes. The only problem is you're not counting by ones. You're counting by, in this case, it was 5/7. So you'd have to finagle it a little bit. So yeah. Just leave it like this. On a test, because yes, I will be letting you guys use your calculator on this next celebration of knowledge. But the work I expect to see on your paper is exactly what we have here. I want to see all of this written out. I need to know what you're typing in on the calculator, but then please, yes, definitely use your calculator. And then just a little warning about that. You may be thinking, oh, good to use your calculator. And some of you guys probably know that you can store stuff on your calculator. And you may be thinking, I'm going to store stuff on my calculator and use that on the test. No, you're not. If you're going to use your own calculator on the test, I'm going to clear your memory. If you have stuff in your calculator that you really don't want me to clear, that's fine. You're just going to have to use one of my calculators where all the memory is going to be cleared. And they're really good at writing questions for the AP test. They do not clear your memory before the AP test, but they have written the questions in such a way that it won't matter. It won't matter what you have stored in there. It's not going to help. Speaking of that, I have this right here. So, this is an actual question from the 2010 AP exam. This is going to seem very hard. Don't worry. The first time you see an actual FRQ, it can be a little scary, like you may be going, holy crap, I'm going to fail. Now, trust me, now that we're in the second semester, the free response questions always involve lots of different concepts from calculus in one question. We now have enough calculus background where we can start looking at actual AP questions. And we're going to be looking at these periodically throughout the semester. As you see them more and more, you'll get to go, oh, it's that kind of question. I know what to do. Or it's that kind of question. I know what to do. But yes, this first time you see it, it's going to seem scary. So I'm just kind of warning you. Don't freak out. It's okay that you may not have any idea what to do on most of this. I will also say, I forgot to say this when I was telling you about the FRQs and like how much time. Most people don't finish the FRQs on the AP exam. Even people that make 5s, most of those people don't finish the FRQs. I don't know why they do it, because then everybody always comes out and goes, oh my God, that was the hardest thing ever, and then you get your scores back. It's like, oh, okay. So anyway, just kind of mentally prepare yourself for that too. Oh, what I want you guys to do, question B is actually the only trapezoidal sum part, but still try to look at all of them. I'm going to give you guys 20 minutes to look at this. And definitely work together. Don't try to do this all on your own. Please. The back does have the answers, but try not to look at the answers. Try to do it this way. But in 20 minutes, we'll come back and we'll look at it together. So let's say 11:05. A little more than 20 minutes.
So if we're actually doing an test, like we're calling it official FRQs, would it be better to just focus on one and try and work completely, or at least do like a little bit of all?
You'll see that there'll be like parts.
Are you gonna sample?
There'll be like parts of each problem.
Good. This is so hard.
I'm going to pause this. All right, so let's take a look. We're going to start at part A. We'll see. We may have time to get to C and D. We may not, but let's at least do parts A and B. I know I told you guys to focus on B, but anyway, let's just see. Part A. So we know that we have this function E of t, and it says the number of entry, I'm looking at the problem above now, the number of entries in the box t hours afternoon is modeled by a differentiable function E. Values of E of t and hundreds of entries are shown. So part A says use the data in the table to approximate the rate. As soon as you hear the word rate, what word should you be thinking of? Derivative, exactly. But be careful on these problems because there's often multiple functions in the problem. So you want to make sure you're taking the derivative of the correct thing. Or sometimes they actually give you a function that represents a rate, and so they've already given you the derivative of something. So anyway, you want to think about that. So it says use the data in the table to approximate the derivative in hundreds of entries per hour at which entries were being deposited. We want to find the rate at which entries were being deposited. We want to find the derivative of the function that represents the number of entries being deposited. What function in this problem represents the number of entries being deposited? What's the name of the function they gave it? E of t. E of t is the number of entries being deposited in the box each hour. And I just lost my train of thought. And so they want us to find the derivative. They want us to find the rate. So really what part A is asking us to find is to approximate the rate, the derivative of the number of entries being deposited of E, derivative of E at time 6. They want us to approximate E prime of 6. Anybody have an idea how we can do that? Say it again. I can't hear you. Not the mean value theorem. Well, maybe it is the mean value theorem that you're thinking of. Be more specific. What do you think? Yeah, it's not really the mean value theorem because I know what you're saying. The mean value theorem tells us there's a place where the derivative has to be the same thing as the slope. We're just going to use the slope to approximate the derivative. And that's not actually what the mean value theorem is, but it's similar. So yeah, E prime of 6 is approximately E of 7 minus E of 5 over 7 minus 5. It's the derivative at t equals 6 is approximately the slope between 5 and 7. And then they gave us values for that. E of 7 is 21, E of 5 is 13. So that's going to be 8 over 2, which is 4. Now, it is a word problem, so get in the habit of putting units on. So E prime of 6 is approximately 4 what? What are my units here? Say it again? Yeah. Hundreds of entries, but there's more. Remember, this is a rate, so hundreds of entries per hour at t equals 6. Sometimes they'll ask you specifically for the units. Sometimes they don't. Don't assume that just because they didn't, they don't want the units. Always put the units in. So any questions about that one? Yeah, Grace. This is really, if you think about it, that's really y2 minus y1 over x2 minus x1. It's the change of the y values over change of x's, so it's slope. It's our slope formula. Any other questions on part A? Part A? Yes, all right. Well then, let's do part B. So part B says use trapezoidal sum with 4 subintervals given by the table to approximate 1/8 times the integral from 0 to 8 of e of t dt. Now be careful because they don't always do this, but they do this often enough. Remember the trapezoidal sum is only going to approximate the definite integral. And I heard people saying this. Don't forget, we're going to have to divide by 8. We still have to divide by 8. I heard several people saying that, so that's excellent. We'll have a 1/8 that we'll just have to worry about at the end. But then trapezoidal sum is what we're going to use to approximate the definite integral. However long that is. I don't know. I'll just go this long. That long. Oops. Now, let's go to the table here. Is my delta x constant? Darn it. So we're gonna have to find the area of each trapezoid individually. Your first delta x is 2, but then the next delta x is 3, and then the next delta x is 2 again, but then your last delta x is 1. So yeah, each trapezoid is its own thing. So if I just do T1 up here, but then I'll put it all below. The first trapezoid would be delta x over 2 And then what are the values of my two bases on this trapezoid? 0 and 4, yeah. So remember, the delta x equals 2. That's what's giving me the 2 on the top. And then this is my b1 and b2, which gives me the 0 and the 4. And then we just keep going with that. So what you should have gotten, and they'll be looking for this on the AP exam. They'll want to see this part, which your delta x over 2 times b1 plus b2. That's the first one. The next trapezoid, delta x over 2 times b1 plus b2. The next one, and the last one. Just write that on your paper because they will want to see that. And then that's showing your work, and then you get your answer, which I'm just going to steal this. Don't forget to divide by 8 though. So we do the trapezoidal sum and multiply by 1/8, and you get about 10.687. So that's the first part of the question. This is the other thing. Also, don't forget to make sure you're answering all of the question. But any questions where that's coming from? Okay. So then it says, using correct units, explain the meaning of this in terms of the number of entries. Using correct units. What does this definite integral actually represent? Actually, let me make it clear. I'm pointing to the whole definite integral, not just the function. Anybody know? I mean, there's two ways you can do this. That's the total number of entries over the 8 hours. This is the total number of entries over the 8 hours. Is that a hand up or are you stretching? I can't tell. Yeah, and I'm actually not even going to put the per hour. It is the average number of entries. It's actually not average number of entries. I have to be more specific. You're very close. In hundreds, yeah. So let's average number of hundreds of entries in the box. During the 8 hours. It's a slight difference between the per hour and the and saying during the 8 hours, because this is at any given time. At any given time, I just look at how many entries are on the box. On average, it's going to be 10.687 hundredths of entries. You can reason your way out through the units in a couple of different ways. I'm at the bottom. I think I have enough room. One way is this. So if you think of the definite integral, now I will go to a new page. This is the explanation of the units. One way is, if you think of the integral, the definite integral represents the area under the curve. Now we don't know what E of t is. It didn't tell us. I'm just going to make something up. It's something like that. We have hours on the x-axis. We have number of entries in hundreds on the y-axis. We're finding the area under the curve. That's what the definite integral represents. So if you think of the definite integral from 0 to 8 of E of t dt, just in terms of units, if it's representing area, think about length times width. It's hours times entries. It's weird, but you can think of it as entries, hours, because it's the number of entries over the 8 hours. It's kind of weird. We usually just say entries, but it's the entries over the 8 hours. But then we're dividing by 8, and that 8 represents the number of hours. So we're dividing by hours. And that's why we end up, whoops, oh my god, I can't spell entries. And that's why our units just end up being entries for that whole expression. So again, this 1/8 gives me the hours. The definite integral is going to be the entries during the 8 hours. So that's just entries. And the other way that you can also think of the units, remember your average value of a function formula. 1 over b minus a times the integral from a to b of f of x dx. That's the average value of f of x over the interval from a to b. Remember when we did that? Last unit? Remember? Yeah. And so it's the average value of f of x. F of x in this case is e of t, which the units for e of t are hundreds of entries. So it's the average value of the number of hundreds of entries. That's why our units are the way that they are. So don't say per hour. It's just the average number of entries in the box. In hundreds. Any questions about that? What? So whatever the value for the integral is, so the part that I've highlighted in green, this represents the total number of entries that were deposited over the 8 hours. Hold on one second. Let me make sure I have E of t right. Oh, no, I take it back. I'm sorry, I'm saying it wrong. So the problem does say that this represents the number of entries in the box. Oh, no, that's, yeah. This does. How do I want to say it? So wait. Now I'm lost on what you were asking because we went to different. Are you wondering? You're wondering what the definite integral represents. Now you just trailed off. I don't know where you were going. So this represents the total number of entries that were in the box over the given time. Well, so if we could, like, imagine at t equal 0.1, there's this number of entries in the box. Then t equals 0.2, then there's this number of... So E of t, it says the number of entries in the box is modeled by this. So E of t is just the number of entries in the box at any time. The integral represents the total it's hard to say. Oh, how would we say this? So like at time t equals 0.1, there's so many entries. At 0.2, there's so many entries. At 0.3, there's so many entries. Now those values are cumulative. So if we could add all of those values together, but the definite integral doesn't go from just 0.1 to 0.2, 0.3. It has all the values in between also. Like it's representing the cumulative sum. It's yeah, I don't know how else to say it. It's not going to be just 2300 though. It's the value, it's including everything below it too. It's hard to say what the meaning of it is. I'll have to come up with a better way of wording it. But you're right, it's not just going to represent the number of entries in the box after 8 hours. Because that's 2300, we know that. That's from the table. It's a sum of all the values. I'm having trouble finding the words. Does anybody have a good way of wording it? I'll get back to you on that one and think of a better way of wording it. But you're right in the way you're thinking about it, that it's not 2300. Let's look at part C real quick. So part C gave us a new function. It says at 8 p.m. volunteers began to process the entries, and they processed the entries at a rate modeled by P. This is what I was talking about. P of T is a rate. They didn't actually call it the derivative of anything, but it may help when we're doing this problem to think of it as a derivative of something. But be careful about that. P is a rate. It says they're processed at a rate modeled by P, where P of T equals, and they give us a nice polynomial. So P of T is this function in the number of hundreds of entries per hour from 8 to 12. According to the model, how many entries had not yet been processed by midnight? T equals 12. This actually is a good one to follow up from what we were just discussing with part B. So we want to know how many entries have not yet been processed at the end of the 12 hours. So this is the rate of entries processed. And again, this is hundreds of. Processed from 8 p.m. to midnight. So we want to know how many are still unprocessed, how many are not processed by midnight. How many entries have not been processed by midnight? Well, we know at 8 p.m. there's 2,300 entries that haven't been processed. They're sitting in the box. So this is the number of hundreds of entries unprocessed at 8 p.m. And then we're going to take away how many they were able to process in the next 4 hours. We need to figure out how many they actually processed from 8 to 12. So we have to take away something. If P is the rate of entries processed per hour, how can we find the number of entries processed? It's like we have to undo the rate. If only we had something that undid a rate. Yeah, the antiderivative. We're going to do the integral of p of t, and we're going to do it from 8 to 12, because it does say t is going from 8 to 12. This definite integral will represent the total number of entries in hundreds processed from 8 to 12. So this is the difference between part B and part C. Part C, we're taking the integral of a rate. So the integral of a rate of change gets you back to a total. And in this case, it's the total of entries. That's why I'm having trouble putting into words what this definite integral represents, because it's not going to be the total number of entries, because it wasn't a rate to start with. So I'm having trouble finding the words for that one. But this one, because it is the integral of a rate, now we're back to the total entries. And then you would type that in on your calculator and you get some answer. Oh, which is just 7. Look at that. I'm looking at the answers. 700 entries. Any questions on part C? We'll save part D. We may or may not have time to come back to it. We'll see. But part D, by the way, just kind of, if you're looking at the answers, trying to make sense of it. Part D says, according to the model from part C, when were the entries being processed most quickly? They want you to find an absolute maximum. And so that's why when you look at the work for finding the absolute maximum, they've made a table of values. You can see that they've plugged in the endpoints. They used a calculator to find the critical numbers. I'll show you how to use the calculator to find the critical numbers. But that table of values that they've given you on the answer key, you see the 8 to 12, those are the endpoints. The other two numbers represent where the derivative equals 0. And then you just plug into the function. But I'll show you that. I'll show you how to figure that out. So we will look at D, because that'll be more calculator stuff we can use the calculator for. Any questions at all on that? The main point is the trapezoidal sum right now. That was big focus. Any questions? Alrighty. Then we are